Okay, so the next example is a very, very simple, overly simple example where we've got a man pulling in a box of 50 kgs. The force he's applying is 250 newtons and it's at an angle of 30 degrees above the horizontal. So the first thing to do is to label the forces that are that we can see. So we always start off with the easy ones. So you've got the weight pointing downwards, or the force of gravity pointing downwards. One thing I didn't mention is the weight is obviously coming from its center of gravity. So by right, that arrow should be originating at the center of the box, assuming that it's got a constant density. So the force of gravity should be coming from there. The force normal should be coming from the floor and coming up vertically into the air like that. And the force of tension should be going in the same direction as the rope at 30 degrees above the horizontal. Okay, so that's our forces labeled, but it's kind of hard to figure out what's going on at that point. So the best thing to do then, step one, this is, in this problem, we're assuming that the floor is frictionless, which I know is a bit ridiculous because if it was frictionless, then the man probably wouldn't be able to pull there at all. But we'll assume that for all intents and purposes, this part of the ground is frictionless, whereas where the man is standing is obviously not frictionless. Anyway, so the free body diagram then for the situation is we draw our box, we've marked in the weight going down, the force normal going up, and then we mark in the force of tension at an angle of 30 degrees above the horizontal. Now, I decided to pull this one out a little bit because our next approach is what we're going to try to do is we're going to sum the forces in the x direction and sum the forces in the y direction, just like we did before. But if you notice, the force of tension is not exactly lining up. So the force normal and the weight are both in the y direction, so there's no problem there. But the force of tension will have to be broken down into the tension that's in the x direction and the tension that's in the y direction. So we break that vector down just like we did before in projectile motion. So we've got the force of tension in the x direction, the force of tension in the y direction. Force of tension in the x direction is going to just be the size of the force of tension times the cosine of the angle 30 degrees. And the force tension in the y direction will be Ft sine theta. Plug in the numbers and that gives us the force of tension in the x direction equal to 216 newtons, and the force of tension in the y direction works out to be 125 newtons, just solving in the numbers, 250 sine theta, sine 30. Okay, now once we've that done, the best thing to do is to redraw the free body diagram. I know loads of you want to try to skip this step, but until you get the hang of it, you really, really need to redraw it. So what we've really done is we've replaced the force of tension with its components. So I'm going to put Ftx here, I'm going to put Fty here. And now we've got values for those, and we've got, so now we're ready for step 4. Once we have identified where those forces are, which direction they're going in, these ones, all the forces now are either in the x direction or in the y direction. So step 4 is now to sum the forces like we've done before. So we start off with the y direction. Now the thing is, I'm not 100% sure exactly what's going to happen. I've written it down like this first, okay? But let's do a quick check. So we just list the forces that are there in the y direction. I know I've got the force normal plus the force of tension in the y direction minus the weight. The whole thing is going to be equal to the mass of the object times its acceleration. Now I've written down here that the acceleration in the y direction is equal to 0. But first thing we really need to do is to make sure that that is the situation. So the easiest thing to do there is to look at the force of tension in the y direction. And we know that that has a value of 125 newtons. That's the force that's being applied by the force, by the man on the box. And what we want to do is make sure that the weight of the box is bigger than that. Okay? If so, it'll stay on the floor. If not, then the man will lift it in the y direction. So the weight of the box is its mass times gravitational field strength. The mass of the box, we said, was 50 kgs. And I'm just going to use 10 for gravitational field strength. Kilograms cancel, and that gives me 500 newtons for the weight of the block. Okay, now this is just by means of a check before I proceed. So the weight is greater than the force of tension in the y direction. So that means that the man is not lifting the box up. Okay, he's actually not able to lift it off the ground. He's applying some force, but not enough to lift it off the ground, which means that the force normal will exist. Okay, so with that said, I will continue on with this equation. So that means that the force normal plus Fty, and we've got a value for that now, and that's 125 newtons, minus the weight, and we've got a value for that, that's 500 newtons, is going to be equal to the mass of the object times the acceleration. And now I'm justified in saying that the acceleration in the y direction is 0, because the man is unable to lift, exert enough of an upward force to lift it at this time. So that means acceleration in the y direction is 0. So just like before, that quantity goes to 0. And that gives us the force normal will be equal to 500 newtons minus 125. And that is 375 newtons, I think. Now, we didn't ask for the force normal, but you will need it later on when it gets to the more realistic examples involving friction. What we're going to have a look at now is to see what happens in the x direction. So, we're now going to sum the forces in the x direction. Just going to have a quick check on the free body diagram. There's only one force that's pointing in the x direction. That's pointing in the positive. I forgot to mention that, of course. That's up, that's positive, that's negative, negative. It's pointing in the positive x direction. And that is the force of tension in the x direction. So only one force, so that means that that's equal to the mass of the object times its acceleration. And it must be accelerating here because I have a net force. There's only one, so there's nothing else to counteract it, so it has to be accelerating. Okay, so now I can just come back and just see, well, what was that? What was the size of it? That was 216.5 newtons. So 216.5 newtons is going to be equal to the mass of the block, which is 50 kgs, times its acceleration in the x direction, which is just going to be its acceleration. So then the acceleration of the block is going to be 216.5 or 50 kgs. And that works to be 4.33 meters per second squared. So we will have an acceleration for the block. It will go to the right at 4.3 meters per second squared. Okay? So best of luck with those types of examples.